So it's past now, so let's get started. Our final talk for this session is by Alexis Toumi on diagrammatic differentiation for quantum machine learning. Please go ahead.
Thanks. So this is a joint work with Richie Young and Giovanni De Felice. And it's on the archive if you want to check out the paper. So let's go over the contents. First, I'll introduce dual numbers. Then I'll show how we generalize dual numbers to dual diagrams. And then I'll apply this to the Zx calculus, and we'll see how we can differentiate any linear map by differentiating Zx diagrams. And then we'll look at differentiating quantum circuits, at differentiating their post-processing with a new graphical notation that we called bubbles, and how bubbles allow us to draw the chain rule with diagrams. And then if I have enough time at the end, I'll go through a very quick demo of our implementation of all this theory. So let's get started with dual numbers. So they were first introduced by Clifford in 1873. He introduced them as another kind of number that he invented along with quaternions. And so here I'll give a definition maybe more abstract than his, using commutative rigs. So a rig, a ring without negatives, is a set and two commutative monoids, plus and times, such that plus distributes over time. So what's the intuition for rigs? Well, they're the minimum structure with which we can define matrix multiplication, and they're also the minimum we need for dual numbers, for defining a notion of dual number. So what are the examples of rigs? Well, the natural numbers are the free rig on one element. Another example would be the positive reals, non-negative reals. And then any field is also a rig. So the reals or the complex would be a rig. A more interesting example would be the Booleans with disjunction and conjunction. So here we have that 1 + 1 = 1. Or the two-element field F2. So the same set, but with XOR for addition. So we have 1 + 1 = 0. So another example of rig, well, we can take all the functions from Rn to C with pointwise addition and multiplication. And that's the one we're going to use mainly in this talk. So, okay, so we have rigs. Now, how do we define dual numbers? Well, we take a rig and then we add, we freely adjoin a new element epsilon. And then we quotient by epsilon squared = 0. So what does it look like? Well, addition is going to be given pointwise. So we have these formal sums, a plus a prime epsilon, and addition is given pointwise, and then multiplication is given by the product rule. So if I multiply two of these dual numbers, well, the real component, if you want, is multiplied, and then I get a times b prime plus a prime times b for the epsilon component. So that's the usual product rule for differentiation. Now, for example, if I take the Booleans 0, 1, I apply the dual number construction to it, I get a new rig, 0, 1, epsilon, and then 1 plus epsilon. So for example, if I do 1 plus epsilon times itself, I get 1 times 1, so 1 plus epsilon plus epsilon. So here it's idempotent, so I would get 1 plus epsilon back. Okay, so now another way of defining the same thing is, or a very related concept is that of a derivation. So essentially it's just a function which preserves sums and satisfies the Leibniz product rule. So if I take the gradient of f times g, I get f times the gradient of g plus the gradient of f times g. Okay, and then if you take a rig with a derivation in this way. In this sense, you get what's called a differential rig. So another way of saying the same thing is that if you map f to f plus the derivative of f times epsilon, you get a rig homomorphism from S into its dual number construction. And then this connection around, if you take a homomorphism from S to D of S, such that projecting on the real component gives the identity on S, then projecting on the epsilon component will give us a derivation. So that's a way of linking derivations in the dual number construction. And so I will use either the homomorphism notation or the dual number construction equivalently. So the motivating example would be the smooth functions from Rn to Rm, with partial derivatives being the derivations. Another example would be functions on F2, so Boolean functions. And now the derivative would be the partial derivative. Derivation would be given by the partial derivative, which in the Boolean case means, well, does f change when I change this component of x, of its input? So essentially, I take the input x, I replace xi by 0, I replace xi by 1, and I take the XOR of those two. So that would be the notion of derivation for the two-element field. We get a different one for if we take the Booleans with disjunction and conjunction, where here the partial derivatives will tell you, is the formula, is the Boolean function positively correlated with the variable? So if I make the variable 0, it's false. If I make the variable 1, it's true. Okay. So why do we care about dual numbers? Well, because they are a fundamental tool for automatic differentiation. So you can check out this Hitchhiker's Guide to Automatic Differentiation. And the intuition is we take a function f defined as a composition of elementary functions, and now we can compute its derivative by evaluating it at a plus epsilon and projecting on the epsilon component of the result. Okay, so now we want to essentially generalize automatic differentiation to work with diagrams instead of just numbers. So we'll generalize the dual number construction from rigs to monoidal categories with sums. So monoidal categories where I can add two morphisms of the same type. So that means I want an enrichment in commutative monoids, technically. So now, what does it mean? Well, I have this plus on every hum set and a 0 on every hum set, and composition and tensor distribute over the sum. So for example, such a monoid enriched monoidal category, if it has one object, then it's a commutative rig. So another example, which is going to be a motivating example, is the category of matrices. So if S has a derivation, then here I can sum matrices, so I'm enriched in commutative monoids. So another example which we care about is the free monoidal category with sums. So you take a monoidal signature, and then you look at the category where arrows are formal sums of diagrams. So now with this, we can define a notion of the dual number construction of a monoidal category. So we take the monoidal category, we add a new scalar, so an endomorphism of the unit, and we quotient by epsilon squared equals 0 again. So concretely, the arrows are going to be formal sums of arrows from C, and composition and tensor given by the product rule. So note, if you don't have symmetry or at least braided, well, you also need that the epsilon commutes with everything. Okay, so now we can play the same game, define a notion of derivation. So derivation is going to be a unary operator on hum sets. So for every hum set, I have a function which sends morphisms to the gradient. And it satisfies the product rule for composition and tensor. Another way of saying the same thing is if I map f to f plus its derivative times epsilon, I get some preserving monoidal functor from C to its dual number construction. Okay, so this correspondence also works the other way around. If I have such a functor from C to D of C, and projecting on the real component gives the identity, then I have a derivation by projecting on the epsilon component. Okay, so if we apply this to dual number, to matrices, we get the same thing as if we take matrices over dual numbers. So dual matrices are matrices of dual numbers. So now a derivation on mat S is going to be the same as a derivation on the rig S. So now we can take this construction and apply it to the free category with sums. So this category with formal sums of diagrams, and we get the category of dual diagrams. So how do we draw these? Well, we're going to draw the gradient as a bubble surrounding the diagram. So the axioms become, if I take the gradient of f then g, well, product row. If I take the tensor of f then g, well, product row again. Okay, so that's a way of depicting gradients of morphisms diagrammatically. So if we fix a monoidal signature and an interpretation for the diagrams, so a functor into mat S, then we say that we have diagrammatic differentiation if there's a derivation on the diagrams which agrees with the derivation on the matrices. So if we interpret a gradient, we get the gradient of the interpretation. So, okay, let's take Zx, for example. So we need Zx diagrams with parameters. So we're going to take the phases of our Zx diagrams to be smooth maps from Rn to R. So we have n real parameters, and phase in such a diagram will be a function from these n parameters to R. So now we get an interpretation for these diagrams in terms of matrices over this rig, which is the rig of functions from Rn to C. So essentially just Zx diagrams, but with parameters. So if you don't have parameters, you get back Zx. And also you can think of a parametrized diagram as just a function from Rn to diagrams. Okay, so what kind of functions can we represent in this way? Well, we can only represent bounded functions. So if we take a function from Rn to C, we can draw it as a parametrized scalar diagram in Zx, if and only if it's bounded. So if it's bounded, I can find phases alpha and beta and draw it in this way. So it's going to be bounded by 2 to the k. And in the other way around, if I take any diagram, there's going to be some bound on how big the value gets with respect to the parameters. Okay. So that's a little technical lemma. And then from this, we can show that if we take affine phases instead of arbitrary smooth phases, then Zx does have diagrammatic differentiation. So first, we take a spider with just one leg, and we show that if we differentiate it, well, we get a scalar with the derivative of the phase, and we'll set this as pi on the phase. And well, this scalar, essentially the idea is we can only draw the scalar if it's bounded, so we need bounded derivatives. And well, affine is kind of an easy condition to ask for to get bounded derivatives. So in the case of affine phases, this scalar will always be a constant. But that's big enough for what we care. General enough for what we care. So now I guess the main theorem of the paper is that Zx diagrams admit diagrammatic differentiation. So what does this mean? Well, that means I can differentiate every generator. Well, for H, for the Hadamard box, it's a constant. So I get derivative 0. The only interesting case would be for the spiders, and using the lemma just above, well, we can unfuse our spider. Then we can apply the differentiation for one-legged spider, and then we fuse back. And that means we can differentiate any spider. Okay, so if we can differentiate any spider, then we can differentiate any diagram. So note, however, that we can't do that for arbitrary phases. So we kind of need the affine restriction, or at least some restriction, because even if you have a smooth and bounded phase, the derivative isn't necessarily bounded. So if you take a phase like sin of theta squared, then its derivative is unbounded and you can't draw it as a diagram anymore. But you can always add more generators. So you take a signature, you add a generator for each scalar that you get as the derivative, and well, the big signature you get has diagrammatic differentiation kind of for free. Okay. Or we can also change the kind of Zx calculus we work with and take algebraic Zx calculus. So I think Zh calculus, as we've seen in the previous talks, would work as well. So if we take algebraic Zx, it's complete for arbitrary rigs. So essentially what we get is that the algebraic Zx of a rig is always has diagrammatic differentiation. And in fact, if a derivation on algebraic Zx is the same as a derivation on the rig. Okay, so one application is we can draw Stone's theorem on one parameter unitary groups in diagrams. So what does it look like? Well, what's a one parameter unitary group first? Well, it's a unitary matrix, parameterized matrix with one parameter. And if you make this parameter 0, you get the identity. And if you compose it with itself, you add the parameters. Okay. And we also need this strong continuity condition. So if you take the limit of diagrams, you get the diagram of the limit, or the limit of the unitaries is the unitary of the limit. Okay. So now, what's Stone theorem in picture? Well, there's a one-to-one correspondence between these strongly continuous one-parameter unitary groups and self-adjoint matrices. And what does the correspondence look like in picture? Well, we have this U of theta diagram, and it's equal to the exponential of h times I theta. So exponential here, we draw as a bubble. Essentially, it's also a unary operator on hump sets. So we take any square matrix and we can take its exponential and we draw it with a bubble. Now, the other way around, the H, the self-adjoint matrix is equal to minus I times the gradient at 0 of U. Okay, so little example. If we take the Zx diagram for that's what it looks like on the left. And if we take its gradient, well, we get this phase, this scalar, the gradient of alpha on the left. We get this plus pi. The plus pi, we can make it go through the spiders, and what we get is a green and a red pi together, followed by our original diagram. And so from this, we can diagrammatically conclude that the Pauli gadget on the left is equal to the exponential of green tensor red pi. Okay. So now, if we want to differentiate quantum sockets, well, we'll need not only linear maps, but density matrices and operators on. So essentially here, I'm defining the category that we've implemented in Python. I'll show a demo of in a minute. So we define this category with objects, pairs of natural numbers. So one for the classical and the other for the quantum dimension of our system. The arrows from one pair to another are going to be given by matrices, parameterized complex matrices. of shape A times B squared to C times D squared. And then composition is given by matrix multiplication as usual. The tensor is going to be defined as this kind of reshuffling of wires. Essentially, we want to keep the quantum dimensions and the classical dimensions in order when we tensor diagrams. Okay, so now that's going to be our semantics. So this is kind of it's a super category of the usual category of density matrices. So we're not even imposing conditions, it's just matrices of a particular shape. Now, what about diagrams? What about the syntax? So I'm going to start with the signature sigma of pure processes. So this could be the Zx calculus. And it's got one object. So I'm going to call it Q for qubit. And we extend it to a bigger signature, CQ classical quantum of sigma, where now the objects are C for classical and Q for quantum. And what are the arrows? Well, we have the pure processes as arrows, and we also have measure and encode. So measure goes from quantum to classical, encode goes from classical to quantum. And now we get a free monoidal category. So all the diagrams we can draw from this, and that gives us classical quantum maps in the sense of Bob and Alex Dodo book. So now, if we have an interpretation for pure processes, we can interpret these classical quantum circuits. Well, essentially, the classical wire is going to be sent to dimension 2 for the classical system, dimension 1, so a scalar for the quantum system, and vice versa for Q. Now we have measure and encode that are defined in the usual way. And we have the interpretation of a pure process is the double of its interpretation. So we take the conjugate, we tensor it with the original thing, and okay, so that's the usual construction. Essentially here, it's a description of what we've implemented. So Leo remark, well, if we have a diagrammatic differentiation derivation for pure processes, we don't necessarily have one for classical quantum circuits. So indeed, if we take the gradient of the double, it's not equal in general to the double of the gradient. So we need more, we need these equations that are called gradient recipes. And so here's the first theorem on these gradient recipes. Well, if we have a one parameter unitary group and its self-adjoint matrix has two eigenvalues plus minus r, then there's a shift S such that, well, the derivative of f can be computed as the difference of f applied to theta plus s and theta minus s scaled by this eigenvalue. So that gives us a gradient recipe in the sense that we can evaluate the gradient of a circuit by evaluating the circuit itself at plus and minus s. So, okay, here's the original paper. And now a corollary, well, classical quantum circuits with Zx diagrams as pure processes admit diagrammatic differentiation. So what does it look like for rotations? So for one-to-one spiders doubled, well, we have that the gradient of alpha rotation tensored with minus alpha rotation is given by this difference with this shift. Okay, so that means we can differentiate not only linear maps, but also density matrices. So also classical quantum circuits written as Zx diagrams. So little technical note, we need to encode this -1 scalar. So either we just add it as a generator or we enrich over a abelian group. So we just take this minus sign for free. So what's an example of application? Well, quantum machine learning. So we can draw quantum classifier, in this case, as a diagram. So here we have an input x and some parameters theta, and we build this quantum circuit on the left, followed by some classical post-processing on the right. And we can differentiate this quantum classifier diagrammatically now. So I guess now one point is that here in this picture, we can only draw the classical post-processing F as a box if it's a linear map. So we only get boring linear post-processing. If we want to go into more general post-processing, we'll need bubbles. So that'd be the last part of the talk. So,
so you've got 5 minutes left, including the question time. So
yep, yeah, I guess I'll just rush through this. So a bubble, essentially you apply a unary operator to some diagram. What's an example? Well, Penrose came up with them to draw covariant derivatives. Méliès came up with them to draw functors. Peirce, 100 years ago, used the same notation to draw negation. And that allowed him to have essentially a complete language for first order logic 30 years before Frege. And so here's the diagram, for example, for every Catholic adores a woman. And now, more interestingly for us, we can draw the nonlinearities of machine learning as bubbles. So, for example, the sigmoid function can be drawn as a bubble, and we can draw a neural network as bubble diagrams. And now, what does the chain rule look like? Well, here it is in diagrams. If we differentiate a bubble, then we multiply in the obvious way. So here's the chain rule with spiders. And the application is going to be, well, we have a quantum algorithm, we have some classical post-processing. Now we can differentiate both in the same diagram. And I won't have time for the demo, but the code is online and I invite you to check it out. Thanks.
Thank you.